So what is a critical value? Critical value of function f is any value of x where the function has to exist. So you have to have a valid value of the dependent variable. Okay? So have to exist. And the derivative is 0 or does not exist. So the function at that value has to have a valid function value, and the derivative is either 0 or does not exist. So what does that mean? If the derivative is 0, what can you say? What can you conclude? What can we say about a function if its derivative is 0? I know Kyle knows. I know Ashley knows. Yes, sir? Not so. No, it's 0, right? So what's not changing? Accumulation is not changing. Either the function itself is constant, okay, or it's just not changing for a moment, right? So for a moment at this critical value, the accumulation is not changing. The rate of change is 0, okay? The first derivative not existing, that's a little bit different. We'll talk about that later. We're going to focus on this first case here. So what's true if, like I said, so if c is a critical value, then the derivative at c equals 0. So this is what we said. F stops or pauses momentarily increasing or decreasing at c. So it's going along, it's changing, and then if you got a critical value where the derivative is 0, then the accumulation is not going to change for a moment. So we think of that as a pause in the accumulation. Okay, so what we're going to do today is we're going to investigate different situations you can have for the first derivative being 0. There's several cases of this happening, and we're going to investigate that. So let's go ahead and hand out the sheets. Okay, so the first one is what we call local max. Okay, a local max. So I want you to check out this animation over here on the right. And first I want you to look at what's happening to the x value in this animation. Just keep your eyes peeled on that black arrow at the bottom and tell me what's our context for x? What is x doing? Yeah, it's just good. We're just going to have x increase constantly, right? And then that gives us a way to really figure out what's happening to y. If we speed up or slow down x or move it backward and forward, then we really can't analyze what's happening to the dependent variable. That's what we want to do. We want to look at the dependent variable. And so to do that, we think about x increasing steadily, right? X increasing steadily. So now we know x is increasing steadily. I want you to just keep your eyes peeled on the pink arrow. Watch the pink arrow. And we want to characterize what happens to the pink arrow. And actually, it's like a sequence of 3 things. It's a sequence of 3 things. So just peel your eye on the pink arrow. Ready? Starting now. So that pink arrow tells us about the dependent variable of f. And what do we see happening? Where's Robert Crutcher? Where's Robert? Noted. Where's Jaiwei Wu? Yeah. Tell me about the pink arrow. What happens first? Okay, so the first thing it's doing is what? What's the first thing the pink arrow does? Nice and loud. Okay, we're starting right now. What is it doing? Is it going left? Is it going right? What is the pink arrow doing at the beginning? Increasing. That's the first thing that happens, right? And then what happens next? Where's Chandler? Yeah. No. That's not the next thing that happens. Watch it. pauses, right? And then, last thing, decrease. This is what we call a local max at this critical value C, a local max. So in the local vicinity of C, what happens? Increase, pause, decrease. So that we're talking about the value of accumulation. Accumulation increases, it pauses, it decreases. So on that first graph there, we can say, so increase, right? And then at the critical value, we have a pause. Rate of change is 0. And then decrease. So if that's the case, now then I want you to sketch the rate of change. Sketch, so you're going to use what we've been learning. Practice what we've been learning. So if the function is increasing and then pausing and then decreasing, what would the rate or the derivative be doing? Sketch it. This is this thing we practiced over and over and over again, right? Where's Yazelin? So tell me when that function is increasing, what can I say about the derivative? So I'm just talking about here over here. When the rate of change is, or when the function is increasing, where would I draw the rate of change? And where? Like here. In positive territory, right? If the function is increasing, the rate of change is positive. So that means the rate has to be up here. If the function pauses, then what about the rate of change? 0. So it's got to make it to 0 there. And now our function is decreasing, so the rate of change is negative. So for local max, this is what the rate of change looks like. Heading down because the positive because the function's increasing, 0 because the function has a pause, and then negative because the function is decreasing. So then, what can we conclude about the second derivative now? So we're looking at this rate graph. So positive, 0, negative, right? That's what we said. Positive, 0, negative. So what can we say then about the rate? The rate, the derivative. Isn't the derivative decreasing? And so if the derivative is decreasing, what about the second derivative? Negative. So what can we say? If a function is decreasing, what about its derivative? Negative. So sketch that. So what would the sketch of the second derivative be? The first derivative is decreasing. Why? Because it's positive and then 0, then negative. It has to be decreasing. So then if a function is decreasing, what about its derivative? Where's Sierra Jones? Yeah.
It would be in the negative.
Right. If a function is decreasing, its derivative is negative. So we're down here like this. So we're putting together this. So really, again, 90% of this is the fact that if a function is increasing, its derivative is positive. If a function is decreasing, its derivative is negative. It all goes back to that, but we're just using it at different layers here, right? So, increasing function, positive derivative. Decreasing function, negative derivative. Well, that creates a decreasing function. So what about its derivative? It's negative. Okay, so now this next one, this is hard to do if I don't give you 4 sheets of paper. But we want to do the next one as if we're not looking. Don't look at the top one, because if you look at the top one, you can do this without even thinking. But we want to think it through. So cover up the first one. Cover it up. Yeah, fold it down. Fold that first one down. So the next one's going to be a local min. And I'm going to erase here. Okay. Next one's a local min. So starting from scratch. First, you're going to determine what's the sequence for a local min in terms of accumulation. Based on that sequence of 3 things happening at a local min, how could you then characterize the first derivative? And then based on how you characterize the first derivative, what can you say about the second derivative? Okay? So kind of erase what we did out of your mind for local max, so we have the new experience of thinking through it again. Go. All right, where's Nicole Ballin? Where's Nicole? How'd that first part go? So tell me about the accumulation. Yeah, so the accumulation function, where we have a local minimum. What happens? She said decreasing, and then pause, and then increasing. Agree? Yeah. So that's what happens. Decrease, pause, increase. This is what characterizes a local minimum. So that being said, how about the first derivative? Where's Justin Horn? Justin. Yeah. So you looked at that for that accumulation function, and what could you conclude about the rate? Negative, okay. Okay. Right, so if it's the function is decreasing, the derivative is negative. If the function pauses, the derivative is 0, and then if the function's increasing, positive. So what will that look like then? We sketched it, yeah.
I kind of drew a diagonal line through the C on the R left, sorry.
Okay, and so I can imagine 2 types of diagonal lines, like this one or this one. So
one fell at the top, so from negative to positive.
yeah, something like this. This is what the derivative will look like at a local min. The function is decreasing, so the rate will be negative, and then the function pauses, so the rate will be 0, and then the function increases, so the first derivative will be positive. Okay, and then going from there, where's Melissa? Imperial. Yeah.
So it's going to be positive.
And why is that? Okay, what is increasing? Yeah. Yeah, the rate now, so the rate is increasing. So for it to go negative, 0, positive, that function has to be increasing, and if a function is increasing, its derivative is positive. So it's just it's always going to be positive up here at a local min. Doesn't make sense. Okay, fold your paper down. Fold it down. So is this the only 2 possibilities? If so, if the derivative is 0, is a max or min guaranteed?
No.
No, there's other situations, okay? So okay, and so the first is a rest stop. Okay, so this is kind of like so on the highway, right? So when you're driving on the highway, and you're heading and you come to a rest stop because you really need to go. So you're gonna get off that rest stop, and then you're really fast at this. So for just a moment, you're gonna go, and then you're gonna get back in your car, and then what are you gonna do? Are you gonna turn around and go the other way? No, you're going to keep going, right? These rest stops, you can't go back the other way on the highway. You have to continue going the same way as you were going on the highway. Okay, so let's take a look at what that looks like. So I don't have an animation for this. So use your fingers, right? So use your fingers. As x increases like this. Oh, I got to do that. So as x increases, what would the arrow on the y-axis do? If you need to use your finger, right? So as x-axis, as the x value increases, what would the y value do according to this graph? So choices are increasing, pause, decreasing. Those are the three choices. So as x increases, what is y doing for a what we call a rest stop type 1? Heading along, rest stop, keep going. The same way you were going. Okay, so what characterizes this? Where's Kaylee? Samson? Yeah.
Well, it's increasing and then it takes a slight pause and then it continues to increase.
Very well said. So it's increasing and then a pause, and now it's going to keep increasing. So now, work out. So this is actually a little more complicated. Really think through this slowly. There's more to this now. So I want you to think through what the rate function would be like, and then generalize about the rate function, and then what would the second derivative be like. There's more to this, okay? It's good thinking exercise. Applying what we've learned. Go. So if you want us to look at your first derivative graph, so you... Okay, that's not right. Oh, that's right. That's right. It's not going to be, it's only going to be 0 for the one pointless. You guys, go ahead and write out increasing, decreasing, positive, negative, where it applies. So like I've done on all the other ones. Here, so on the axes and on the graphs, write out where is it increasing, decreasing, positive, negative, where you can say that for sure. Okay, where's Michaela Smith? Michaela, how'd it go? Tell me about the first derivative.
So the first derivative would be a parabola that touches at C.
Okay, so a parabola is a very specific thing, so it might not be a parabola, but have what I know you're imagining the right thing. So what are you imagining? Don't use the word parabola.
It's in the positive region.
Okay.
Decreases.
Right.
And then it hits 0 at C.
Right.
And then it's still in the positive region, but it increases.
Like this. So what's happening? So the first derivative is doing what? First it decreases first. Sorry, it's positive. And then it's 0. And then it's positive again. And that comes right from the function increasing, pausing, and increasing. Okay? But we can also say, what else is happening here? At first it's positive, but it's decreasing. and then it pauses, right? So it's 0, but it's also pausing, right? It's also pausing and then increases. So we have decreasing, pausing, increasing. What does that mean for the second derivative? Where's Samantha Reynolds? Samantha. Okay. Right, so if a function's decreasing, then pausing, then increasing, then its derivative is going to be negative, 0, positive. It's negative, and then 0, and then positive. So what can we then generalize about the second derivative? What can we say about it? Yeah.
It's increasing.
It's increasing, right? So then, it should have said that. It didn't. I'll write it. So the second derivative is negative, and then 0, and then positive, but generally also, it's also increasing. So then, what can we say about the third derivative at a rest stop? So we got a function that's increasing. What about its derivative? Positive, if we wanted to. So we could say that the third derivative is positive. Okay, does that all make sense, right? So there's a lot going on there. But we're using the same basic principle over and over and over again. So it's just on multiple layers of derivatives, okay? All right, fold and forget. Fold and forget. And go. Think it through, right? Think it through. Just don't base it on the last one we did. Okay, where's Brooke Speckman? Brooke here? On a roll here. All right, tell me about the accumulation if we've got a rest stop like this.
So it would be negative up to the 0 and then go negative.
I think you're talking about the first derivative. What about just the function? So just what's the actual accumulation doing?
So it's decreasing.
Uh-huh.
Then it takes a pause.
Yep. Right. So here's another way we can have a critical value. This is the fourth way. A pause where it's decreasing, and then a pause, and then decreasing again. And then what you originally said was about the first derivatives. Go ahead and say it again.
It starts off negative and goes up to the 0 and then stops there, takes a pause there, and then goes negative.
Right. So if it's decreasing, pause, decreasing, its derivative will be negative, 0, negative. So what will that look like? Next person here. Where's Giovanni? Yeah. Yeah, so yeah, what if I were to sketch this graph being negative, 0, then negative?
Yeah, it would start from the negative.
Yep.
Go up, touch C, and then come back
Good.
down.
And so if it does that, now we can analyze that. That first derivative, what's it's doing? Where's Anya? Holland. Karan Shah. Yeah. So now, So- no, I want to know what this is. So we know this is negative, 0, negative, but then we can also conclude what about this? What's happening to this, the first derivative then? Increasing and then pause and then decreasing. So that first derivative is increasing and then pause and then decreasing. And so what can we say about the derivative, the second derivative, or the derivative of the first derivative? If it's increasing, where's Jonathan Kinkoff? Not here? Sierra Jones again. There you are. Tell me, so now I know that this function, this rate function is increasing, pausing, and decreasing.
So it would be in positive because of the increase, but it would be heading towards C0.
Yep.
And then it would be C, and because of the decrease, it would be negative.
Yeah, so it's positive, 0, and then negative. And then we can look at that graph and we can talk about the third derivative if we want. What's true about this graph then? If it's positive, then 0, then negative. Decreasing. Its derivative then is negative. Third derivative is going to be negative at a rest stop type 2. Okay, so these are the 4 ways that you could have a momentary pause, or the first derivative being 0 for a moment. This is the 4 different ways that could happen. Okay? Any questions on that? So unfold and save it and practice it all again. Okay? Okay, so here's a function. Here's a function. We want to apply what we were just talking about there. At all these given x values, we want to find out what the function is, function value, what the value of the first derivative is, and what the value of the second derivative is. So let's just do this. We'll do the computation for x equals 1, just so we would know how to fill this table out if we needed to. So everyone, I want you to fill out the table for the row where x equals 1. Go. Fill out the table for the row where x equals 1. And then I'll show you all the rest of the values. So we just should know what we're talking about here. Where's Edgar Chides? Edgar, so did you get g of 1 yet? 2. Did you get 2? People are nodding. And how did you get that? What did you do? Plug in 1 to the function, right? All right, so then this next one, g prime of x at 1. Did you get that? Where's Mei Chen? Mei Chen. Not here. Haley, Nadone. Yeah. So what would you do? So if I wanted to find g prime of x at 1, tell me how you would do it.
So you would derive, so it would be the 4x cubed minus 18x squared
4x cubed minus 18x squared
plus 24x.
plus 24x. We die for derivatives like this now, right, after the mastery. Like, this is like falling out of bed, right? This should be so easy, right? 4x cubed minus 18x squared plus 24x minus 8. And then what do? I want to find the derivative at 1. So I'm going to plug 1 into that. What do you get? Who's done it? Shout it out. Someone got it. Positive 2 again? 28. No, it's a negative 2. No. Yeah, 1. 4. Be 28 minus 26. Isn't that negative 2? Oh, minus 26, right, 2. I'm not very good at math. Okay. All right. So then what I'm going to do for the second derivative, it's going to be 12x squared minus 30x plus 24. What do you get? You get 0. Good on the row for number 1. Now we could do this for all the rows, but I'm going to give this to you. Okay? Here's what we get. So now based on these numbers, we want to understand what is the function g, the accumulation function, doing in the vicinity of these, or in the local neighborhood of these x values at that moment, right? So at the moment x equals 0, what can you conclude about what's happening or what the accumulation is like? And then can you make a little sketch? Make a little sketch of the function g near x. You want to do this for all these situations. So see how many you can do in about 3 or 4 minutes, and then we'll regroup, okay? See what you can do. So based on the values and what we've been talking about, sketch g in the local vicinity of these x values based on the values of g, g prime, and g double prime. Work together, okay? And if you've got questions, ask. You're not making the graph of g. Okay, so last you trying to sketch. No, you're not trying to sketch your g. Don't try to do that. Just around, we're just doing this one piece at a time. Just a little piece, just sketch g near x. Like I'm going to do it right here on the screen. And then I'm going to do this one. Just sketch g near x. Don't try to do the whole thing. Okay? Just one point at a time. So for instance, if the first derivative is negative, what does that tell us about g? Decreasing. If the second derivative is positive, what does that mean? That the rate is increasing, or the original function is doing what? Turning up. Remember? So we've got a decreasing g that's turning up. What does that look like? Draw it with your finger. So right around 0, it's going to look like this. That's all I wanted you to do. There we go. So do that for each point. So Now at 0.5, what can you say if the first derivative is 0 and the second derivative is positive? So what would it look like right around g? First derivative is 0. Okay. It looks like, okay. But it's turning off the whole time, right? Before and after.
Yeah.
So, yes. This is our local min.
Yeah.
You want to use the sheet that you made earlier, so you can use that too. Okay, let me talk through them, okay? I'm going to talk through them. So, if the first derivative is 0, we have a pause. But it's a pause where the second derivative is positive, so that the function is turning up. So there's a pause and it's turning up. What would that be like? What is that? It's a pause where it's turning up. Where's the pause? Only right there at that, right there. So what is that? What do we call that? This is a local min. It's the very bottom of that, right? It's where there's a pause, but the whole time it's turning up. Second derivative is positive. If you look on your sheet, local min, this will match exactly what we sketched out for local min. 0 first derivative, positive second derivative. Okay, next one. Function is, if the first derivative is positive, function is increasing, but the rate is decreasing. So that means that the function is turning down, but it's increasing because this is positive, so it's going to look like this. Increasing and turning down, right? Increasing and the rate is decreasing. Increasing and the rate is decreasing. It's like that. Next one. This tells us that the graph is increasing, but the second derivative is 0, so it's not turning. This is called an inflection point. So we would need more information. But it's increasing, right? So it's not a rest stop. It's not a rest stop because it's going up. It's either going to look like this, so it's going to pause going up and then like that, right there. Or, now it's not a rest stop because it's going up. It's not 0 first derivative, it's a positive first derivative. So it's one of these two. That's called an inflection point. It changes from turning up to turning down, or from turning down to turning up. So it's called an inflection point. This next one, graph is increasing and the rate is increasing, right? So the function itself is increasing and the rate of change is increasing. which means it's increasing, turning up. And the last one, the jury is out. So yeah, but we know, what is this? First derivative is 0 and the second derivative is 0. We saw that. Those are rest stops. So it could be like, but there's actually, it could be, it doesn't have to be a rest stop actually. There's actually situations where it could be like this or like this too.